Creatine regeneration facilitates rapid ATP turnover during muscle contractions. While well documented, it represents only the final stage of a much larger metabolic economy. Inside the body, creatine is one of the most metabolically expensive compounds to manufacture. The internal assembly line required to maintain baseline levels imposes a significant daily tax on systemic resources. Providing this compound externally acts as a metabolic sparing agent. It alters how the body allocates its internal resources by signaling the system to halt its own internal production. The systemic benefits of supplementation stem from the massive biochemical workloads it relieves. By meeting the demand through external sources, you lift a primary manufacturing burden off your internal organs. To quantify this structural cost, we must look at the body's primary biochemical factories, the kidneys and the liver. The process begins in the kidneys. To initiate synthesis, the body pulls two amino acids, arginine and glycine, and fuses their structures. This fusion creates an intermediate compound called guanidinoacetate, or GAA. Once formed, GAA migrates to the liver for final conversion. Fulfilling the body's baseline requirement for creatine requires this cycle to run continuously, creating a permanent structural tax on your metabolic capacity. Modern human metabolism typically operates on a 5-gram daily shortfall of glycine. While the body requires roughly 10 grams for optimal function, internal production and standard diets rarely close the gap. This deficit is largely a result of modern dietary patterns. We no longer consume the connective tissues and collagen-rich foods that served as primary glycine sources for our ancestors. The demand for creatine makes this shortage worse. The internal assembly line siphons off a massive portion of this already limited glycine pool to manufacture GAA. Under ideal conditions, this glycine would fuel collagen turnover in your joints and produce glutathione, the body's master antioxidant. Instead, those systems are forced to operate with whatever remains after creatine production takes its share. Every molecule of glycine consumed to build internal creatine is a direct withdrawal from the body's antioxidant defenses and tissue repair systems. The resource cost increases once the newly formed GAA reaches the liver for the final step of synthesis. Here, the body uses S-adenosylmethionine, or SAM. This molecule is the body's primary methyl donor, providing the chemical groups necessary to finalize the conversion into creatine. The scale of this reaction is massive. This single step consumes approximately 40% of all methyl groups derived from SAM in the entire body. Data from the American Journal of Physiology confirms that this is the largest methyltransferase reaction in human biology. It demands more resources than every other methylation reaction combined. This creates an intense opportunity cost. Vital processes like DNA repair and the production of dopamine and serotonin are forced to compete for the remaining 60% of the SAM pool. The body is chronically underfunding genetic maintenance and vital neurological stability simply to sustain its own internal creatine production. We can observe the systemic stress of this process on a standard clinical blood panel by looking at homocysteine. Every time SAM donates a methyl group to a reaction, it leaves behind a molecule of homocysteine as a byproduct. Because creatine synthesis is the body's largest consumer of methyl groups, it is the primary driver of homocysteine production. High homocysteine levels often indicate that the internal creatine assembly line is overworked, creating a state of chronic metabolic inefficiency. This entire metabolic drain can be halted with a daily 5-gram dose of exogenous creatine monohydrate. When you supplement, systemic creatine levels rise. This triggers a negative feedback loop that tells the body it no longer needs to manufacture its own supply. The body responds by downregulating the enzymes in the kidneys and liver. The entire internal assembly line shuts down, instantly stopping the drain on glycine and methyl groups. Research in the American Journal of Physiology shows that this intervention directly reduces GAA levels and lowers systemic homocysteine by relieving the methylation burden. Supplementation acts as a command code that allows the body to power down its most expensive metabolic factory. As the creatine synthesis pathway closes, the resources previously trapped in that loop flood back into their intended physiological pathways. The 40% SAM loss is recovered, reallocating methyl groups to fuel DNA repair and neurotransmitter synthesis. Simultaneously, the glycine pool recovers. Amino acids lost to GAA production now flow into collagen turnover and glutathione production, enhancing joints and antioxidant defenses. This shift moves the body from a state of chronic resource triage into a state of optimal homeostatic balance. This strategy is particularly important for those over age 30, when the body's natural capacity for tissue repair and antioxidant defense begins to decline. Clinical data supports a continuous daily dose of 5 to 10 grams of simple creatine monohydrate. No loading phase is required to trigger the sparing effect. Stacking this protocol with N-acetylcysteine or direct glycine optimizes the glutathione pathways, maximizing the body's detox capacity. If supplementation stops, internal synthesis will resume. The enzymatic pathways remain intact and will reactivate once the external supply is removed. Supplemental creatine reduces the manufacturing load on the liver and kidneys. By providing the compound externally, you allow the body to redirect its resources towards the natural regenerative programming that was previously sidelined by the cost of internal synthesis.